In this video, we are going to continue our discussion of periodic trends. So we left off with atomic and ionic radius, and now we're going to move on to ionization energy, which is the energy required to remove an electron from a neutral atom. So with ionization energy, it always requires energy. It's always a positive value, okay? So when you are yanking an electron away from an atom, it's costing you energy. It's an endothermic process. Also pointing out that when you have a neutral atom and you lose the first electron, that's ionization energy 1. And then when you have the cation, you can lose a second electron, and that's ionization energy 2. You don't lose them both at the same time. So they are calculated independently. So there's no 2 electrons from a neutral atom. It's always 1 electron at a time. So let's compare ionization energies here and maybe think about how we could use orbital diagrams to explain the differences between sodium and magnesium. So you see that sodium is at 496. That's how many kilojoules per mole it costs in energy to take an electron away from a sodium ion, or sodium atom, excuse me. And it takes 738 kilojoules per mole to remove 2 from magnesium. That's not even double here. But then it's almost 10 times the amount of energy to remove the second one from sodium, whereas it's maybe double to remove the second one from magnesium. So why might that be? Well, remember that if sodium loses 1 electron, it's now at a noble gas configuration, which means that it is at the lowest energy and it's very stable. And so that is favorable. Whereas with magnesium, if you lose 2, it then is at that stable configuration. So that makes sense as to why that would be energetically favorable. So you might be thinking, like, how in the world is this an endothermic process? I just saw it catch on fire. Well, it is not so much the actual act of taking the electron away, but what happens to the electron after it leaves. And so the products have so much less energy than the reactants that's why it's overall a release of energy, even though the actual act of removing the electron from the sodium atom costs energy. Same for magnesium. Okay, so let's do some predictions with the concept check. So what would have the larger ionization energy between oxygen and fluorine, and what would have the larger one between O and S? So you can see the values here, but I want you to use your orbital diagrams to explain this. Okay, so you might want to pause this, sketch out your orbital diagrams, and see if you can justify those values. Okay, let's take a look. So why does oxygen have a larger ionization energy than sulfur? Well, if you look at the orbital diagram we have, or the electron configuration, either way, you see that for oxygen, we have 2s2 and 2p4. And then for sulfur, we've got 3s2, 3p4. So the shielding from sulfur is greater than for oxygen, but the charge for the nucleus is greater for sulfur than for oxygen. However, this is so much bigger. And remember from Coulomb's law that the distance between 2 charges partially determines their attraction. So if these are separated by a large distance, then they aren't going to be as attracted to each other. And so it really comes down to the larger energy shell with the larger volume. And then as the radius increases, the ion attractions decrease, so it's easier to remove the electron. So the trend is that it gets easier as you go down the periodic table. And now remember, these are positive numbers, so as they get closer to 0, that's more favorable. So what about fluorine and oxygen? Let's compare these guys. So we have our energy, energy configuration, electron configuration here. So we have our 1s2, 2s2, and then we have 2p4, 2p5. So they have the same shielding, but fluorine has an extra proton in the nucleus. So the Z effective would be greater for fluorine. So for oxygen, our effective nuclear charge is 8 minus 2, which is 6. And then for fluorine, it's 9 minus 2, which is 7. And so that electron on fluorine feels a greater pull. So it's harder to overcome that attraction. So that's what actually has to happen. You have to put in enough energy to overcome the attraction the electron has for the nucleus. So ionization energy, it first increases as you go up and to the right. And so just remember that means that if it increases, that means it's harder, right? So it's more positive, it's more difficult. So it's harder to remove an electron as you go up and over. So now let's kind of talk about the opposite idea, which is electron affinity, which is the atom's ability to attract an electron. Now it's not exactly the opposite, but it is very similar to that. So with electron affinity, we have our fluorine and it's obtained an electron here. This releases energy most of the time. It's usually a negative value, and we'll talk about why it's not always in a minute. So you have your atom, you add an electron, and you get a negative charge. So again, we're adding them one at a time. So this would be EA1, EA2 would be adding 2 electrons. So this depends on how easily the atom can accept it, and the trend is not as regular as it was for all of the others. So here is the electron affinity values for some elements, and you see as it gets more negative, it means it's easier to accept. So these are very negative, very, very positive. These are the most negative. Why would this be? Well, if they accept 1 electron, they are now at this noble gas configuration, which lowers energy. So the energy is released upon accepting an electron. Some atoms are perfectly happy, perfectly low energy, and are unreactive. There's nowhere for the electron to go. And so that would have a positive value because it was harder for example, helium to accept an electron than fluorine. So let's do a concept check. Let's use electron configurations to explain this trend in electron affinity. So we're going to compare nitrogen and phosphorus, and we're going to compare sodium and chlorine. So what's going on here? Well, let's take a look. So with our nitrogen, we're at 1s2, 2s2, 2p3. So if you add an electron, you're actually adding it. These are all aligned very well. So if you add one, what's happening is you're kind of messing up this nice parallel spins. There's going to be more repulsion here. So that's going to be less energetically favorable. But with phosphorus, it's so much bigger that there's room for that electron, so it's not as big of a deal. And if we look at our sodium and our chlorine, we would see that sodium, all of these would be filled, and then it would just be 1 in the 3s sublevel. And so if you lose that 1, then it just looks like neon. So makes sense. And then for chlorine, it is all but 1 is full. So you could imagine if you just add 1 more right here, if these were all full and just 1 more, so that would be why that would be so highly negative. So electron affinity, the trend is like this. However, it's not as clear as, it's not as consistent as the other trends. So this graph actually shows how it increases as you go across the row, but then it drops back down. So it's not as simple as saying, well, magnesium must be better than calcium or than potassium. So you kind of have to think about, think a little bit more about what's going on in here, because it's just not as straightforward. And when we talk about, if you start talking about electronegativity, the ability to attract electrons within a bond, that's a little more steady. But we're talking about the electron affinity outside of a bond, so just a plain atom to accept an electron. And the trend is generally like this, but it really looks more like